Hi grade 9s, welcome to the last part of Unit 7. Remember that we're combining Unit 7 and 8 because they were both short units, so I combined them to make a sort of a regular sized unit. In any case, for rotations and rotational symmetry, 7.6. In 7.5, we dealt with reflections, which was essentially just, sort of a mirror reflection or a fold over a line of symmetry to make a similar shape. This time, we're going to be actually rotating, so we're going to be turning objects and seeing if, by turning them, we can match up the shapes and if there's any symmetry that way. So the place that we're going to start here is we're going to look at this plus sign. Okay, so we've got a plus sign, and if we were to rotate this plus sign about the middle, we have to do it by the middle. That's the only way we can tell. So by the middle, if we rotate this thing 90 degrees, we end up with a shape that is exactly the same. So this point up here would have been rotated, this point up here would have been rotated and would have ended up right there for 90 degrees, just like this line would end up this way. So we've got one 90-degree rotation, which takes us to an object that looks exactly the same as the original object. And if we rotated another 90 degrees, so we flipped it essentially upside down now, it still looks the same. And if we flip it another 90 degrees, we turn it one more quarter turn, it looks the same, and then we can get it right back to the original, in which case we've done a complete 360-degree circle. We've rotated all the way around. So we were able to match this shape by turning it 4 times, right? So there was 1, there was 2, there was 3, and then back up to the original is the 4th turn. So we say that a shape has rotational symmetry when we can rotate it and end up with the original shape again. So what we have to consider is that it can only be a rotation of less than 360 degrees. Because once you rotate it a full 360 degrees, then it sort of becomes the second spin. We've already tested it out, right? If we spin this object all the way around once, and then we spin it 90 degrees again, we get back to rotation 1. And we've already identified rotation 1. So that's why you only spin it once, and really 359 degrees. So it's the number of rotations that you can make to match things up that determines how many times the shape will coincide with itself. In this case, it was 4 rotations. So we call that rotational symmetry, and it only has to match up with itself at one time. This object happened to match up with itself 4 times, but it only has to match up one time in order for us to say that this object has rotational symmetry. There's another term that's called the order of rotation. The angle of rotational symmetry. That's what I'm looking for. The angle of rotational symmetry is the 360 degrees that you can possibly spin the object divided by the number of times that it matched up. Say the number of times that it matched up is the order of rotation. So that's just the number of times the shape coincides with itself, or in other words, looks the same. So when we rotated this first object, we were able to do it 4 times. Okay, we were able to do it 4 times in the 360 degrees. So the order of rotation would have been 4, and the angle of rotational symmetry is always a full 360 degrees divided by the number of times that you can rotate it and still find symmetry. So 360 degrees in this case divided by 4 is 90 degrees. So we say the angle of rotational symmetry is 90 degrees. So again, the new terms there, rotational symmetry, an object has rotational symmetry if we can rotate it anywhere from 0 to 360 degrees and match up the shape. So it has rotational symmetry or it doesn't. It's a yes-no question. The order of rotation is the number of times you can rotate it while making the same shape. So in this case, we could rotate it. There's 1, from here to here is 1, 2, 3, 4. And then the angle of rotational symmetry is just 360 degrees divided by the order of rotation. So let's do that with a couple of other shapes. A shape that requires a rotation of 360 degrees to return to its original position does not have rotational symmetry. So basically we're saying if you flip an object in a complete 360 degree spin around the middle, and the only time it looks like the original is when it's spun all the way around once, it does not have rotational symmetry. it has to do it somewhere between 0 and 359 degrees. So let's look at some examples down below, and let's decide if these have rotational symmetry, and if they do, can we determine what the angle of rotational symmetry is and what the order is. So this first object, now it's not going to be perfect because I kind of just tried to trace. You see, I kind of tried to trace over what you've got in your workbook so I can spin it around a little different. To identify where my starting point was, I just put a line from the red dot in the center to one of the corners, so I can kind of keep track of how much I'm spinning it. So this is essentially a 300, we're going to do a 360 degree spin, but we're going to try and do it in increments that lets us find out what the angle of this thing is. So I'm just going to draw a line there, and I'm going to note that that is 120 degrees. Okay. This is a triangular sort of, object here, but how many sides? 1, 2, 3, 4, 5, 6. Okay, so I guess this is some sort of weird, what's 6? Hexagon? Weird hexagon. But this angle is 120 degrees. By the way, the only reason I know that is because I know that these dots are set up in a way that if you go horizontal and then you go up and toward the left, that's 120 degrees. So that's the only reason I know that. I didn't actually measure it or anything. But it's going to help me out because later when we figure out the angle of rotational symmetry, it should have some relation to that number that I just said. Okay, so let's just take a look at this object, and I'm going to spin it, and we're going to see if we can sort of match it up. Again, it's not going to be perfect. If I spin it this way, okay, I'm not close. I've spun it from there to there, so that's roughly 90 degrees, and nothing's matching up. If I spin it a little bit more, though, I get to there. Now, again, I said it's not quite perfect because my the image is slightly stretched, but if I just move it down a little bit, you can see, yeah, that's pretty darn close to matching up. Okay, so if my drawing were perfect, it would match up. So there is 1. Okay, there's an order of 1, so we've been able to spin it 1 time. Then if I keep going, there's another one right there. Okay, so there's another one right there. Again, it's not perfect, but it's pretty darn close. So that's 2. And then if I spin it up to the original again, that counts. Okay, the third, or the spin that gets you from somewhere to the original counts as part of the order. It only doesn't count if you start at the beginning and have to spin it all the way around. We don't consider those objects to have rotational symmetry, and that's what this part up here says. A shape that requires a total rotation of 360 cannot have rotational symmetry order 1. So we only count that last spin if there was another section that was matching. So there's the 1. Okay. There's the 2. And then that goes from the second rotation back up to the original, which is the 3rd. So what that means is this object does have rotational symmetry. The order is 3. We were able to spin it 3 times. And rotational symmetry, I guess we could put yes. And then we should also put angle of, and I'll just put RS for rotational symmetry. Well, it's going to be 360 degrees divided by the 3. Okay, and that's going to be 120 degrees. Remember before when I said this was 120 degrees? Essentially, this point rotates until it meets that point, and that is 120 degrees. So that's how that relates to your starting point of this particular point. And every other point will go 120 degrees too. This one will go from here to here. That's 120 degrees. And, well, really, that's the only one. Like, this one will go to there. This one will go to there. And then we're kind of back at the beginning. So that's what the relation was between that initial 120 degree angle that I drew. When we came down here and did the angle of rotational symmetry, it worked out to be 120. All right, let's move on to the next one. So once again, I've got a little marker here to show us where the starting point is. So I'm just going to spin it. It doesn't look like anything's close. Okay, that's a 90-degree spin. Clearly, that's not matching up. So I'll keep going. And that's not working. That's not working. Okay, there we go. So I've spun this thing 180 degrees. My line originally started there, and I flipped it all the way around, and now it's down there. That's 180 degrees. So we know we've got rotational symmetry, and we can't make it match anywhere else until we get up to here. So that's the original again. So what we did is we were able to spin it twice, right? We spun it once till it was upside down, and then we spun it once more to get up to the original. So that means that our order for this one, I'm just going to change colors here. Our order for this one is 2. That's not green. Green. Our order is 2, and our rotational symmetry is yes. And then our angle of rotational symmetry is going to be the 360 degrees divided by the order of 2, so the number of times we were able to spin it, and we get 180 degrees. Does that make sense? Well, yeah, it should, because this line here, okay, it only matched up when it was down here. Well, what's a straight line? A straight line is 180 degrees. And if you don't like looking at it that way, let's just look at it with a line of symmetry. If we put a line of symmetry right here, and I asked you, is this object symmetrical, or is half this object symmetrical? When I rotate it upside down, when I flip it, because when you're folding it, you're really folding 180 degrees, right? When I rotate it, does this point here end up on top of that point there? Yeah, it does. It clearly does, right? So that would be 180 degrees. So that's what this is really describing. Is the plane of rotation? How far does it have to go in order to make one match? All right, let's look at this other one. So this last shape, a little different here. If I rotate it, okay, nothing's matching up, nothing's matching up, nothing. Okay, that's 180 degrees, still nothing. And then nothing, 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 nothing. The only way I can make it match is going right back up to the original. And we said up here, if you have to do a complete 360 in order to match it up, it does not have rotational symmetry. So where it says order, we don't say it has order 1. It doesn't have it, okay? Not applicable. Does it have rotational symmetry? No, it does not. So we don't even bother doing the angle of rotational symmetry because it has no rotational symmetry at all. Okay? So the rotational symmetry question has to be a yes-no. Either it does or it doesn't. If it does, then you can figure out what the order is, and then you can calculate what the angle of rotational symmetry is. All right, let's look at a few more objects here. It says rotate pentagon A, B, C, D, E 90 degrees clockwise about the vertex E. Well, that would be super easy to do if I actually had this thing labeled, and I don't. So let me label it. Dunbar. You wild man. Okay, it was supposed to be labeled as A, B, C, D, E. Okay, that's important because it's asking us to rotate it 90 degrees clockwise about vertex E. So we have to care about vertex E right there. All right, let's think about vertex E. If we have to flip this thing 90 degrees, that means every single line here has to move 90 degrees. So it's going to rotate 90 degrees. Well, what happens when you rotate a horizontal line 90 degrees? When you rotate a horizontal line 90 degrees, okay, let's just look at it the side here. There's a horizontal line. What happens when you rotate it 90 degrees? Okay, it comes like that, and it becomes a vertical line, right? So a horizontal line turns into a vertical line. Why is that important? Because we can kind of help ourselves out here by saying, well, that's a horizontal line there. So I know in my finished product, that's going to have to be a vertical line that's 2 boxes long. And the same thing applies for a vertical line. What happens when you rotate a vertical line 90 degrees? It's going to turn into a horizontal line, so that we know that BC and ED, those are both vertical lines. So we know that those both have to be lying horizontal in our finished version. So it's just one of those little things you can do to make a mental check. Okay, so we have to rotate every line 90 degrees. How are we going to do that? Well, let's just look at A to E right now. Okay, so if I'm going across from that point to that point, and we can assume that this is a perfect square here. We're going to have to assume that. If I rotate this line 90 degrees, it's going to have to come up. Remember, 90 degrees is a right angle, right? It looks like a perfect L. So if I rotate this line 90 degrees, that means I have to rotate it this way, and that point A is going to end up right there. So that's going to be A prime. I might do those into different colors just to illustrate that it's our new shape. So this point right here is going to be A prime. So it's basically going to be the new A. E does not change because we say we're rotating about vertex E. When we rotate about something, it means that that particular point does not change. So E is going to be the point that does not change. Where does B go? Okay, well, this whole object has to rotate. Okay, this whole object has to rotate. So the line that was AE, okay, is now AE. A connects to B, and A connects to B by one diagonal box. So A connects to B by one diagonal box. That must mean that B prime is right there. So let's join that one. A lot of this is just visualizing, right? Some people are really good at it. Some people it takes a lot more practice. But promise me, if you know, I promise you rather, if you work at it, you will get better at it, and it won't seem quite so difficult. Okay, what does B connect to? B connects to C. And this is one of those ones where we can do a quick check on. We said that if a line is vertical and we rotate it 90 degrees, it has to be horizontal. So this line from B prime to C prime needs to be horizontal, and it needs to go 1, 2 boxes. So if this is B, well, it's not going to work if we draw it this way. It's going to be the wrong shape, right? So we have to go 1 over, 2 over. So we know that this is going to have to be C prime right there. Okay. And now you can see the object starting to take shape, right? C and D, well, they're connected. They're 2 boxes long, and it's a horizontal line, which means in my new version, it's going to be a vertical line. Well, it's clearly got to be right there. So this point right here is both B and D prime. So it's B and D prime. And then, the last part is E and D. Well, we know E doesn't change, and D connects to E, so D prime must also connect to E, so it's just going to be there. And that other mental check we did, right? E, D is vertical here. So if we rotate it 90 degrees, it has to be horizontal, and it is right there. So there's our rotation, and we can rotate around any point, and the point that we rotate around doesn't necessarily have to be on the object. It could be out here somewhere. This is one of those ones where it probably makes sense to have a couple pieces of paper, and what you do is you draw an object on one piece of paper, and then you put another piece of paper over top of it, and you trace, and then you can spin the top piece of paper, and it makes it so much easier for you to visualize what's happening here. For instance, I think I made this an object that I can spin. So if I was going to say I have to rotate this object 90 degrees, and I was having a little trouble making the points like I did up here in the green, if you've got this traced version, you can take the top version, you can just do this, and you're like, okay, I need to spin this 90 degrees, and I know that that is 90 degrees. So my final shape should look like that, and look, it does, right? So that's why it's important for some of these that you make yourselves, some manipulatives with a piece of paper. It just helps you visualize it. If I was asked to rotate this particular object 180 degrees, okay, well, if I start at the top, 180 degrees, I have to go all the way to the bottom, right? So I'm going all the way to the bottom. That would be a rotation of 180 degrees, and this would be a rotation of 270, and then we're back to the normal 0 degrees there. So that's why I recommend that you use some paper to help you out with some of these, especially if they're complex objects and you're just having trouble visualizing how to spin it in your head. Specifically how to spin it around a point, right? Because we weren't spinning this object around the middle. Okay? When I do it like this, I'm spinning it around the middle, right? The middle of the object is what it's spinning around, just like the middle of a clock. But that wasn't what this question asked us to do. It asked us to spin it around this corner right here. Okay? So that's why I made it a little bit more difficult. All right, B, let's rotate this trapezoid 120 degrees counterclockwise. So clockwise is toward the right, and counterclockwise is to the left. You'll notice that the dot pattern on this is different than the square pattern. These are what are known as isometric dots. They're in, basically they're in triangular form. So it's going to be, this would be, this angle here would be 60, that would be 60, and then if you did this, that'd be 120, and the straight line is 180. It just makes it a little easier to draw triangular shapes and shapes with 120 degree angles. So I also believe I put some copies of this dot paper that you can print off as well if you need a little assistance. All right, rotating trapezoid FG. HJ. So this is, once again, forgot to label it, FG. Do it in black, just like I did the other one. FG, HJ. Okay, what are we supposed to do? Let's rotate it 120 degrees counterclockwise about the vertex F. So this is the vertex that's not going to change. Okay, we have to spin this whole thing around F. But we also have to decide, well, what's 120 degrees? Because every line has to spin 120 degrees or rotate 120 degrees. Well, I said specifically that these dots help us make 120 degree angles. So anything that is an oblique angle here is 120 degrees. So if we've got a straight line and we want to turn this 120 degrees, essentially what we're doing is we're taking this line and flipping it to there. How far away is the G from the F? Well, it looks like it is 1, 2, 3. So the space of 3 dots. So this is 1, 2, and it looks like it's going to be a little bit out there. I don't have quite enough dots for this thing. So you're just going to have to forgive me because it's going to look a little bit wonky. So this was 1 dot, it's 2 dots. So I'm going to say right there, that is now point G prime. Okay. And the line between F and G still has to be there. So let's join that with F and G. All right, what's our next point? Okay, what does G connect to? G connects to H. Okay, how does G connect to H? Well, it goes 1 and then 2. So the length of 2 of these lines. The only problem is I don't have these spaces up here to get that perfectly. So I'm going to have to sort of estimate it a little bit. It's going to be lined up with this. Let me just think here for a second. It's going to be lined up with not that dot, but this dot. So it's going to be up here, right there. Sorry, I wish I'd drawn my paper a little differently. And that's going to be H prime. And that has to be connected with a line. And then what is H connected to? H is connected to J. Okay, now we're not dealing with 90-degree angles, so I can't say that this JH is going to be a vertical line or anything like that. I don't know. Okay, it's going to be 120 degrees different. So I guess I can tell you that that's going to be 120 degrees from horizontal, but I don't know that helps us all that much. The difference between J and H is 1 dot to another dot. So that's going to go to right here. So that is J prime, and I'll just line that up again. And then the last one's easy because you know it has to go right back to the beginning again. So it should be a 2 dot distance between J prime and F and J and F. So that's a 1, 2 dot difference. So there we go. So that looks like we have rotated that 120 degrees counterclockwise around point F. Now, if I just spin this off just to double check, okay, if I spin this and I line this line up with the dots on the 120 degrees and I move it, yeah, it looks like even though I didn't have the dots there, we lined it up pretty well. So again, some people are pretty good at just visualizing these things and knowing where the points naturally need to end up, and other people are, they do a little better if they've got something that they can see and spin and turn. So that's why I recommend sort of the 2 pieces of paper to help you out with that. Example 3, create a rectangle by connecting points 4, 1, 2, 1, 2, 4, 4, 4. All right, let's just do that. That shouldn't take us too long. First shape's going to be in black, so that's going to be A is 4, 1, so there's 4 and 1. And then B is 2, 1, so there's 2 and 1. C is 2 and 4. D is 4 and 4. There we go. So that was A, B, C, and D. And that makes a rectangle. Well, why don't I just make it a rectangle? That'd be easier, wouldn't it? A rectangle tool. All right. Rectangle tool, starting there. We're going to there. Just missed it. All right, so we've got our rectangle here, and we're going to rotate it, and if you notice up here, we're rotating everything by vertex A. So basically we're grabbing the corner by A here, and then we're spinning the rest of the object around it. So let's look at this first one here, which is a 90 degrees clockwise about vertex A. So if we're dealing with a 90-degree rotation, it means that any line that is vertical is going to end up horizontal, and any line that's horizontal is going to end up vertical. So all the points still have to connect each other, even though we're going to add new points. The only point we're not going to have to add is A, because A stays as A. So A connects to D, and we know that D's got to come all the way this way, 90 degrees, so that it lies down flat. And 1, 2, 3. So a D is 3 away from A. So let's just 1, 2, 3, and we'll put a new point here, and that point is going to be D prime. All right, then we know that D connects to C, and this horizontal line is going to be vertical now because it's got to rotate up 90 degrees, and it's 2 away from D, so it's going to be 2 away from D prime as well. So 1, 2. That's going to be C prime, and then C is connected by B the same way that A was connected to D. So it's going to be 3 horizontally. So 1, 2, 3. So this point right here becomes B prime. Then we just got to connect the dots. So that shape right there. Ooh, pretty rough there. Let's see if I can do a better job of that. This shape right here is 90 degrees clockwise about vertex A. The next one is 180 degrees clockwise about vertex A. And actually, the first time I did this question, I screwed it up because what I did was I rotated it around the point between B and A and ended up with a shape down here right below it. But that's not right because we've got to rotate it all the way around point A. And what that means is instead of spinning 90 degrees, which would take us up to a vertical, we've got to spin this thing all the way around like that. So that's going to be 180 degrees. So the A point, as it did before, is going to stay there. If we're spinning something 180 degrees, it means the horizontals are still going to be horizontal and the verticals are still going to be vertical. But this B point has to come all the way up and around to the other side. So how far away is it from A? Well, it's only 2 away from A. So to get it all the way over and around the other side, it ends up right there. And that's going to be B prime prime. We're going to get a little cluttered here. And if that's B prime prime, this C has to come all the way up and over and around and down too. So let's start looking at how far away C and D are from A. So if we flip this all the way around, A and D still need to line up, and it still needs to be a vertical line, which means D has to be below A. So 1, 2, 3 away. So it's going to be 1, 2, 3 away. So this is going to be D prime prime. And then C prime prime's got to be connected to B, right? So C prime prime has to be right here. So now we've got the 4 points, right? A is the shared point, as it was before. And then B connects to C. C connects to D. Well, C prime prime connects to D prime prime. And A connects to B. So that takes us to 180. And then our last one is, what color? Green. So our last one is going to be 270 clockwise about vertex A. So we spun it to 90. We've spun it to 180, and now we've got to spin it. Hopefully I don't make too much of a mess of this. If that's 180, then we've got to spin it all the way to 270, right? So this line between A and B has to end up vertical at the 270 point. Now another way to think of it is you could rotate, instead of rotating 270 degrees towards the clockwise, it's also the same thing to rotate it 90 degrees the other way, right? So instead of going all the way around toward the right clockwise, you can just start at the, you can start and go 90 degrees counterclockwise. It equals out to the same thing. So A is still connected to B, which means we have to go, let's see, 2, right? So 1, 2. Now working with 270 degrees is very similar to working with 90 degrees. Anything that's horizontal is going to end up vertical, and anything that's vertical is going to end up horizontal. So A still connects to B, so this becomes B prime prime prime. And then, so A is still connected to B. B is connected to C by 3, and it's 3 away, right? So 1, 2, 3. So that becomes C prime prime prime. And then C is connected to D by 2, right? 1, 2. So that becomes D prime prime prime. And then you can just connect the dots back to A, C prime prime into B prime prime. And I'm going to be perfectly honest with you. First time I did this, first time I had done this question, I haven't done it for quite a while, and I spun the first one with A being the vertex, and then for some reason I forgot, and I started spinning it from the point between B and A, which gave me the wrong results. And actually, a student pointed it out to me, so it was very, very sharp of them. So just don't make the mistake that I made. Take your time and make sure that you're spinning the object, you're rotating the object around the right point. So these ones, again, probably best if you work with a little piece, two pieces of paper. Sketch out your object on the bottom piece of paper, then copy it by tracing on the top piece of paper, and then you can spin the top piece of paper around a certain point. You can also, you can stick a pin through it so that it's anchored on point A or the tip of your pencil or something like that. It just makes it a little easier to visualize it. So that's always a good way of checking what you're doing. So if you have any questions with those, please don't hesitate to email us and let us know if there's something that caused you a problem. If not, best of luck to you. And we're getting close to Unit 8 here. I think we're going to start Unit 8 in a couple days. So take care.